Everybody know what a center of mass is? That's sort of correct. What's the center of mass in this pen in my hand? The middle? I don't think the middle is the center of mass. See, because if I put my finger in the middle, it falls. It's where it balances. So that's what we mean by center of mass. The center of mass is where would you put your finger on the object to make it balance. So there's the center of mass for that pen. Okay. So as little kids, you played with center of mass a lot. Probably. When you were a little kid, how did you do center of mass? Teeter-totters are a very common example of center of mass. All right, so a teeter-totter looks like so. Okay? And what do you do with a teeter-totter?
Jump off one side so your friend falls.
You jump out one side so your friend goes wham and hits the ground really hard and bounces. It's fun to watch, yes. I agree. It's even better when you have kids and they're that much lighter than you, they really go flying. Of course, you got to take them to the doctor, and that's not so much fun. That's true. Sling the child. Oh no, not me. So, when we're dealing with mass, what are the units that are used for mass? Kilograms commonly are used in the metric system. What if you're in the U.S. system? Pounds. No, pounds is not mass. Pounds is weight. What's mass?
So it's not grams?
It's grams if you're, well, usually it's kilograms in the metric system, unless you're using, they do sometimes use centimeters, grams, and seconds. So sometimes you work in CGS. Usually it's kilograms. No, it's not joules. It's not ounces. No, newtons. What's newtons? Newtons is the force. So if you're dealing with the metric system, newtons is the force, kilograms is the mass, and the acceleration is, what units are acceleration in? Meters per second squared. Okay, so if we're dealing in the U.S. system, force is pounds. Acceleration is in what units? Usually feet per second squared. Okay, so we have this formula. Force equals mass times acceleration. So in the U.S. system, force is in pounds, and mass is in feet per second squared. I'm sorry, I said mass, didn't I? I meant acceleration. Acceleration is in feet per second squared. So what are the units on mass? Other way around. To get mass all by itself, you would divide by feet per second squared, wouldn't you? So mass, the units on mass is pounds divided by feet per second squared.
Just go by the metric system.
No, because I like this word. And these are known as slugs. Mass in the U.S. system is in slugs. You never heard it? See, you learned something new today.
My friend was telling me this one time. I just completely forgot.
Mass was in slugs.
That was funny.
All right, so let's say we have a teeter-totter here. And I'm going to sit on one end. Well, I'm not going to sit on one end. My son is going to sit on one end. My son is sitting down here. Let's say this distance, how long is our teeter-totter? 50 feet? That's a big teeter-totter. Let's be more realistic. Let's say it's 12 feet. And my son is sitting on this end.
That makes it 24 foot.
Yeah, 12 feet and 12 feet. Yeah, that's 20. It's still pretty big. 24 feet. That's a pretty long teeter-totter. So that's
Big
a,
kid one.
what's that?
Big.
Right, it's a big kid one. You know, my son's 16. He's pretty big. And then I'm going to sit on the other end somewhere, and I want to sit somewhere so that my son and I balance. So I'm going to be sitting here somewhere. My distance is going to be X. I don't know where I'm going to sit, but I know it's less than 12 feet. And I happen to know that my mass is about 6.56 slugs. You all know how many slugs you are, right?
Oh, yeah.
My son's a little smaller than I am. He's about 6.42 slugs. So what I want to know is, where do I have to sit in order for us to balance, for us to be able to both sit, be in the air and just hang out for a while? You have to use what rule? And what's the lever rule? Anybody know the lever rule? Okay, it's a proportion. What has to happen is the mass times the distance on the left side of the fulcrum has to be the same as mass times the distance on the right side of the fulcrum. So we would have to have 12 times 6.42 would have to be 6.56 times x. That's easy enough, right? So we grab our calculator. 12 times 6.42 divided by 6.56. I would have to sit pretty close to the end, actually. I would have to sit about 11.74 feet from the fulcrum. It's pretty close to the end for us to balance. Questions on that? All right, now I'm going to ask a slightly different question. I've got the same teeter-totter. My teeter-totter is still 24 feet long. My son is sitting on one end. He still has a mass of 6.24 slugs. And I'm sitting exactly at the other end, and my mass is still 6.56 slugs. But this is a special teeter-totter. This is one where you can move it. Right. So now my question is, where do we put the fulcrum?
Go back to the formula, and x is now coming different. X is right there. X was how far you had. So it's going to be a proportion.
Okay. And I think Brian had the right idea. I know before I had to slide in a little bit, didn't I? About a quarter of a foot. So it seems as though for this to balance, what should happen? The fulcrum shouldn't be exactly in the middle. Where should the fulcrum be? About a quarter of a foot. All right, so let's see if that works. So if the fulcrum's right here, then this distance would be, well, we moved it a quarter of a foot, so that would be 11.75 feet. And on the other side where my son is sitting, that would be 12.25 feet. Does that work? Well, if that's going to work, what has to happen? We have to have 64 or 6.24 times 12.25 would have to equal 6.42. Yep. Did I say 6.24?
Yeah.
I wrote the right thing. 6.42 times 12 and a quarter would have to equal 6.56 times 11.75. Let's see if those are equal. 6.42 times 12.25. On the left we have 78.645. And on the right we have 77.08. Close.
Is it because of that 100 that we skipped? You have to use the exact answer for it?
I don't think that 0.01 is going to make that big a difference. Probably because of the math? No.
Can you write out the formula? The formula for the one we did before. Should we do our next stuff now?
Well, the problem we're going to have,
Yeah.
I think we could write out a formula.
This could be a proportion.
All right, so let's see if we can write out a formula. Let's see. So again, my son's over there, 6.24, 6.56. The fulcrum, we're going to say, goes right there somewhere. Okay, so let's call this distance right here x.
So that's going
So my distance, that's exactly right. My distance would be 24 minus x, wouldn't it be? Because this whole teeter-totter is 24 feet long. So I think there's the way to solve that. You get the right idea. You had to move it to the right. You moved it a little bit too far, I think. All right, so we can have 6.42x equals 6.56 times 24 minus x. All right, so that's 6.42x equals 6.56 times 24, 157.44 minus 6.56x. Move the x's over, so 6.42 plus 6.56, 12.98 is 157.44, and we divide 157.44 divided by 12.98.
That's x.
So x should be 12.12 feet, which means that the fulcrum is 0.12 feet off center. Questions on that? All right, well, now we're going to have fun because let's make the numbers a little bit easier, though. Now we have this same long teeter-totter. This same long teeter-totter. This teeter-totter is still 24 feet long. But now I'm sitting at this end, and just for fun, let's say I'm 7 slugs, just to make the numbers a little bit easier so I don't have to deal with all these decimals. And my oldest son is on this end, and he weighs about 6 slugs. And then, let's see, my other son, he's going to sit here, and he weighs about 5 slugs. And then we'll put my daughter over here. She's about 2 slugs. And then we'll put my wife somewhere near the middle. She's about right there. She's also about 5 slugs. Now how do you find the balance point? Very carefully, that's correct. You move people around until it works?
Yeah.
No, that's no fun. You want to be able to sit right down and have it balance.
I like guessing.
You like guessing? All right, so what are we trying to find? We're trying to find the balance point. What's another name for the balance point? We're trying to find the center of mass. All right, so what we need to do is we need to come up with a technique for finding the center of mass. Okay? So let's, just for fun, we're going to put the fulcrum right here, and we're going to call this x equals 0 for now. Okay? It's not going to work. No, I agree. It's not going to balance. Okay? Is this teeter-totter going to fall down to the left, or is it going to fall down to the right? So I'm on this end. Am I going up or am I going down? I'm going up. I'm going to space. You sure?
I think you're going up.
You think I'm going down?
Yeah.
How do we find out? We do some math calculations. Okay, very good. What math calculations do we do? No, we don't do any integrals here. Not yet. We'll get to some integrals. I need to know more information, actually, and we are going to do some summations. What do I need to know? I also need to know, not only do I need to know the masses, what else do I need to know?
Where they are.
I need to know the distances. Okay, so we said this teeter-totter was 24 feet long, right? So I'm at x equals 12, and it looks like my daughter's at about x equals 10. Okay. Here's my oldest son. My oldest son, he's at x equals Negative 12. Why would we call that negative 12? Because it's to the left of 0. So he's at x equals negative 12. My middle son here, he's at x equals negative 7. And this one, my wife is at x equals negative 1. Okay, so now, how am I going to determine which way the teeter-totter is going? Am I going up or am I going down? Absolutely. I take the mass times the position. Mass times position, that'll give me the force on this end. And then I do the same thing over here. All right, so the right-hand side, I have 12 times 7. How much is 12 times 7? 12 times 7. 84. And 10 times 2? 84 plus 20. 104. So I've got 104 on this side. Over here, what's 12 times 6? 72, and then 7 times 5? 72 and 35? 107. And then 5 more would be 112, except this one we would call negative, wouldn't it? So am I going up or am I going down? I'm going to go up because there's more force on this end than there is that end. This number, this 112, is bigger than this number 104. So I'm going to go up, definitely. All right.
That's if x equals 0 is directly in the center.
And that's with x equals 0. That's if we put the fulcrum right in the middle of the teeter-totter, then I'm going to go up. Correct. So to make this balance, absolutely, we would have to move the fulcrum to the left a little bit to make it balance.
Can we move it past, I think that was your wife right there?
That may have to happen. It may have to happen that we have to move it way over here. That's a possibility. It may be that maybe my wife should be right on the fulcrum. That's a possibility too. I don't know. How do we figure that out? Try what? Guess and check. All right. I think with this many numbers, I think guessing and checking might take a little while.
Is this some sort of min and max relationship?
No, not really.
Is there some sort of equation?
There's some sort of equation. Yes, there is some sort of equation. What sort of equation is there?
Not one that I know.
What's that?
Not one that I know.
Not one that you know. No integrals. Yet. We will come to some integrals.
What about summation? She said
We will use some summations. All right, so here's what has to happen. Let's forget about these numbers for a minute. Let's just say we have several masses sitting around. Okay? What we would do is we would take, we have how many? We have 1, 2, 3, 4, 5, 6. We have 6 of them here. We would take the sum from I equals 1 to 6 of xi times mi. Where what does xi stand for? Xi is the position. So for example, this one might be -5, this one might be +4. So xi is the position of each mass, and what's mi? The mass of each mass. Correct. Now, we're going to let x be the center of mass. That's the symbol we're going to use for center of mass. Now what we're going to do is we're going to take this whole long teeter-totter and we're going to slide it. We're going to slide it by however much x bar is. Okay? So what happens if I take this point right here and I slide it by x bar? Maybe I have to slide, I don't know which way x bar is. Maybe we have to slide it to the right. So if this is the point -5, and I slide it x bar to the right, then where would that be? It would be 5 plus x bar. Negative 5. Okay? Actually, it would be negative 5 minus x bar. How come? Because think of where x bar would be. If I'm sliding this to the right, if this is 0, and I'm sliding it to the right, where's x bar?
It's that way.
X bar is really a negative number, isn't it? So if I'm going to shift this teeter-totter to the right, that means the center of mass should be over here. X bar is a negative number. So we would have the sum from I equals 1 to 6. We would have xi minus x bar. We have to shift by x bar. We would actually just take xi minus x bar times mi. And if this system is in balance, what happens when I add all these things up? I would get 0. It would be perfectly in balance, right? All the negatives would cancel out with all the positives. This would be 0. All right, so I'm going to do a little work here. On the left-hand side, this is the same as the sum from I equals 1 to 6 of xi mi minus the sum from I equals 1 to 6 of x bar mi equals 0. That's x sub I. So this is the position of each individual thing. So what did I do? How did I start with one summation and end up with two summations?
You can break it apart since they have the same summation.
They had the same summation.
So that
I distributed the mi through, and then since it's the same summation, I can split it into two summations, can't I? If I want to add a bunch of things and subtract a bunch of things, that's the same as adding and subtracting them. I just split it into two things. All right, we're getting close now. This is the sum. I equals 1 to 6 of xi mi equals the sum from I equals 1 to 6 of x bar mi. What did I do there? I just took this one and moved it over to the right, didn't I? That's all. I just added that number. That's some sort of number. I don't know what number it is. I just added it to the other side. This is the sum from I equals 1 to 6 of xi mi equals x bar times the sum from I equals 1 to 6 of mi. What did I do that time?
X bar the other time.
And why can I move x bar to the outside? It's just a number. So all I really did is factor it out. I had x bar m1 plus x bar m2 plus x bar m3, so on and so forth. I just factored the x bar out. So here's our formula for x bar. X bar would be the sum from I equals 1 to 6 of xi mi divided by the sum from I equals 1 to 6 of mi. It's 1 to 6 this time because I drew 6 little dots. If I drew 14 little dots, then the sum would go from 1 to 14. If I drew 1,000 little dots,
I just do a limit that.
right, if you get 1,000, you're not going to deal with it probably.
What xi is xi the position or is mi the position?
Xi is the position.
Okay.
Mi is the mass of each of the dots that I drew. M for mass. All right, this thing on top, this is called the moment about the origin. And it's called capital M, M sub O. And this thing on bottom, what's the thing on bottom? What did I do? The sum of mi's. It's just the sum of all the masses, isn't it? This is the sum of the mass. All right, so you remember at the beginning we talked about the title had moments, it had centers of mass, and it had something else. Centroids, whatever those are. We'll get to that. What's a centroid? All right, so here's our formula. To find the balance point, you add up all the xi's times mi's, and then you divide by the total mass. Okay, so back up to our teeter-totter here. How do I find the balance point? To find the balance point, x bar is going to be, according to this formula, I take each x value, multiply it by each m value, and then add them up. So I'm going to have 6 times negative 12, plus 5 times negative 7, plus 5 times negative 1, plus 2 times 10, plus 7 times 12.
Wouldn't you just add negative 112 plus 104?
I could simply add negative 112 times plus 104 since I already did all that work. Absolutely. So that makes the top a lot easier to figure out. The top is negative.
Negative 8.
Negative 8.
Sorry, negative 8.
And then I'm going to divide by, I simply add all the masses. The masses were 6 plus 5 plus 5 plus 2 plus 7. So it should be negative 8 divided by 25. So that's where I should place the fulcrum for my family to balance happily. Negative 8 over 25. I should move the fulcrum 8 over 25 feet to the left. Yes?
So x is the distance from the center or distance from fulcrum?
X is the distance from the center.
Okay. I'm just trying to write this out.
Right.
Isn't x bar the average?
X, that's why we use the symbol x bar. When you take statistics, x bar stands for average. So what you've really done here is you've really averaged all of the masses based on their position.
I was looking at that going, I'm sorry.
It's exactly an average. That's really what it is. And if you've ever had statistics, x bar is always used for average.
Is there a symbol other than x bar, like in physics, for center of mass?
I don't know.
Or is it just called center of mass?
This x bar is called the center of mass. It is possible that in physics they use a different symbol. They do use different symbols in physics than we use. I don't know why. Why can't they do it the right way? I don't know. All right. Well, that makes it pretty easy, right? So let's just say we have a number line here. And there's 0. Let's put a bunch of masses on the number line. So where do you want to put the masses? And how much mass? All right, so you want some slugs on the right. How many slugs? And how far out do you want it? All the way. All right, so we're going to, all the way, we're going to have 2 slugs. And let's say this is 10. And this is going to be minus 10. And then right about here we have some slugs. This is at 5. How many slugs do you want there? 7 slugs there. How about, that's at about a half. How many slugs are sitting at a half?
1.5.
1.5 slugs. And then over here at negative 9 we have some slugs. 3 slugs. And then you wanted 7 slugs? All right, we'll put 7 slugs at negative 4. Is that enough slugs, or should we do some more? Plenty of slugs? All right. Where do I put the fulcrum to make that balance?
In these equations, will you ever have, like, say if somebody's sitting on someone's lap, if you have 2 on top of each other?
If you have 2 on top of each other, what happens? Then you would just add their masses. So if my daughter's sitting on my lap, then together we would be 9 slugs.
Is there ever a limit? Like, say you had 9,000 slugs on the right. Is there a limit?
If you had 9,000 slugs on the right and only 2 on the left,
Yeah.
then I think it would... Well, we'll try it. I don't know.
I think you actually have to have the fulcrum.
I think the fulcrum would have to be...
Yeah.
Right, so we'll try it. We'll find out. All right, let's do this one first. All right, so to find x bar, how do we find x bar?
Multiply the number of slugs by the position.
Negative 9 times 3, plus negative 4 times 7, plus 1/2 times 1.5, plus 5 times 7, plus 10 times 2. So you take each mass, multiply it by each position, add them all together, and then divide by, add up all the masses. So that would be 3 plus 7 plus 1.5 plus 7 plus 2. You grab your calculator. Negative 9 times 3 minus 4 times 7 plus 1/2 times 1.5 plus 5 times 7 plus 10 times 2. I got negative 38.35 divided by 3 plus 7 plus, oh, I should have done this in my head. That was foolish. Oh well, 20.5. Negative 38.35 divided by 20.5. You need to move the fulcrum 1.87 feet to the left.
I don't understand why the top's at 0.5.
This, which top?
The, yeah, right there. 38.35.
Because I had a 1/2 times a 1.5.
And 1/2 times 1.5 is 0.75. Or, no, 0.75, not negative.
Oh, I don't know. Did I type it in wrong?
I just don't know.
Oh, I did. I typed in 5.7 instead of 5 times 7. How about positive 0.75? I typed it into my calculator wrong. Divided by 20.5. 0.0366 feet. It needs to move 0.03 feet to the right. Barely needs to move. And it'll balance.
Nearly balanced.
Nearly balanced. We were close right from the beginning.
You're never going to do that to us, right?
Do what to you? Make you sit on the teeter-totter?
Do all this work and then eventually get to the end and realize it's balanced?
I probably would never give you one that's already balanced. That would be mean, wouldn't it?
Yeah.
If you do all that work.
It would cancel out and we'd all freak out. Like,
Yep.
It canceled what we do. What about the 9,000 slugs with one on the other side?
All right. So, here's 0 again. Where do you want the 9,000 slugs?
All the way at the end.
All the way to the end.
Right at the end. They're like a tower.
So how far is that?
10.
10? So that's 10, and we have 9,000 slugs. And then are we putting a mass on all the way on the other end? So that would be at negative 10. And we're going to have 2 slugs?
Sure.
All right. So where's the balance point? Well, x bar would be negative 10 times 2 plus 10 times 9,000 divided by 9,002. All right, so that would be negative 10 times 2 plus 10 times 9,000 divided by 9,002. X bar would be 9.99555 feet. So in theory, you can do it. If you can measure something that accurate so that you're only away from the end by 0.00445, that's pretty small.
The material is probably great.
Well, maybe not. You only got 2 slugs going all the way down this end. That's not very heavy. So,
Is there ever going to be a situation where we're going to get 10 or we're going to get the max? Or are we just going to get...
no, the balance point always has to be somewhere in the middle. It just has to be real. How much weight is 2 slugs?
64.
It's about 64 pounds. That's correct. How do you know 2 slugs is about 64 pounds?
Just the conversion from acceleration.
Right, because force equals mass times acceleration. The mass is 2. The acceleration is 32. So 2 slugs is about 64 pounds. So you'd have about 64 pounds sitting on the end of this thing. It might hold up depending on what you made it out of. I'd be more concerned about the 9,000 slugs sitting on the other end.
It's like a gross pile.
because that's about 288,000 pounds.
Is that like how much is that in tons?
Imagine seeing that balance at
How much is that in tons? How much is a ton?
2,000
2,000
pounds.
pounds?
144 tons. It's 100. I don't think
140.
How many-
1,440 tons.
I don't think.
Oh no, I missed a zero. It should be 144 tons.
How many elephants is
So it's the weight of the, whatever you call it.
Teeter-totter.
Teeter-totter. Does the weight of the teeter-totter matter at all, or is it because it's even on both sides?
All right, that's an excellent question. Does the weight of the teeter-totter matter at all? Maybe. And my answer is maybe. I've assumed it hasn't. And what I mean by maybe is, when we are doing this problem, we're assuming that the teeter-totter is made of something of uniform density. Which all that means is it's the same all the way across. If you cut a foot of it, no matter where you cut that foot off, it's going to have the same weight. But that doesn't necessarily have to happen, does it? You could, in theory, have a teeter-totter that's thick on one end, and then the board gets thinner and thinner and thinner as you go.
I was just asking if it mattered, like, if the board itself was like 100 pounds, if it was like 5 pounds, it mattered. As long as it was even all the way
As long as it's uniform all the way across, it doesn't matter.
Okay.
But if your board is not uniform, then absolutely you would need to take into the board into account too.
as long as it can hold 9,000 slugs?
Well, in this case, we need a board that can hold 9,000 slugs also.
So we're just going to assume that this board is about the size of a building.
And keep in mind that we need to be able to fit this 9,000 slugs in a distance of 0.00445 feet.
Yeah, I'll say 4 pounds is what's left over for that.
So I guess there's a whole bunch of it off the edge maybe and about to fall over. All right. Now then, what happens if you have a two-dimensional system? So, for example, I might take my calculator and say, where's the balance point on my calculator? And what I mean by balance point is I don't mean lay my finger across it and just have it balance in one direction. I really mean be able to put my finger there. Ooh, that's close. Be able to put my finger somewhere on the calculator, have one little point where it balances in all directions. I'll never find it. I'll drop my calculator and break it. So I won't do that. How do you do that? So that's what I mean by center of mass on my calculator. The one little point where I could hold my finger and the calculator would stay up. Somebody always tries this when I mention it.
She knocked it out of my hand. I was trying to do it.
Sure, she did.
This one would be the sum of the x plus the sum of the y.
Very good. What you have to do is you have to find the balance point with respect to the x-axis. Second time he was just trying to put it down. That's even funnier. You have to find the balance point with respect to the x-axis, and you have to find the balance point with respect to the y-axis. Okay, so how do we find the balance point with respect to the y-axis? What are we going to do? Well, for each blob, each mass, what do we need? We need its mass and we need its distance from the y-axis, which would be the x value, wouldn't it be? All right, so we call this one my. My stands for the moment with respect to the y-axis. So for my, we would take mass 1 times x1, because we want the distance from the x-axis, plus mass 2, x2, plus up to, I don't know how many masses we're going to have, mn, xn. Okay, so we call that my. That's the moment with respect to the y-axis. And then we also need the moment with respect to the x-axis. So what would we call that? mx. Oh. See, sometimes these things make sense. What would mx be? I would need the mass times the y value. I would need the mass times the distance from the y-axis. So I would need m1, y1 plus m2y2 plus up to mnyn. And then we would have simply the mass itself. What would the mass be? M1 plus M2 plus, you just add up all the masses. Okay. And then finally, we can find our center of mass, also known as the centroid. We call it x bar, y bar. How are we going to figure out x bar? Oh, you found your balance point. Yeah, but you're cheating. You've got your thumb laying down, so you got a big fat surface area to lay it on.
It's impossible to do it on a bigger surface area.
It's not. There is a balance point. You ought to be able to balance it on the end of your pen.
Yeah, if you can like
Not move ever or breathe.
Yeah, if you cannot move and not breathe, then you should be able to do it. All right, how are we going to find x bar? For x bar, we're going to take something and divide by something. What goes on top? My goes on top for x bar. Very good. It's a really good guess. Well, you had a 50-50 chance of being right. And what goes on bottom? Nope, no, that time you're wrong. M, just the sum of the masses goes on bottom, right? If we're trying to find x bar, why do we use my? That seems backward to me. All right, so because my meant the distance from the y-axis, and for the distance from the y-axis, we used the x numbers.
Are we going to get like a point that way it's my and
Yes, so we will get one point where we should put our finger and hold it, and the whole system will balance for us. And then y bar would be mx divided by m. So the notation here gets confusing. My gives you your x bar number. Mx gives you your y bar number.
Is this balance of a like calculator thing going to be on the test on Monday?
No, this will not be on the test on Monday. This will be on the test 2 weeks from Wednesday. Almost had it, didn't you?
Can we talk about test Monday?
Sure. What do you want to talk about at the test on Monday?
Anything? This is on Monday?
It is on Monday.
Other than the integrals that you gave us on the lab list.
Arc length and surface area. Sure. All right, so we will finish up. I didn't think we would be able to finish this today anyway, so we'll finish this on Monday.